Start recording. So, where we left off last time, we had this funky thing. We make a shape and then hold down space, and our little clock would start going, and it would, fly off in this arc very slowly. And so what we've got here is we have basically. Oh, turn off my heater so it's not making noise. We've got these initial values for we've got this constant value for acceleration, and that's 9.8 Earth gravity going downwards. That's fairly straightforward. And then we've got this 50 and 25 meters for our initial velocity, which is very fast. And then we run this thing, and it takes like forever for this thing to start going down, and it seems to go very slowly. And the reason is we've kind of ended up in a situation where our zoom level is like 1 pixel per effectively meter if we're going by 9.8 meters per second. If we zoom in a whole bunch and make a shape, then it flies off the screen. So what we might do, maybe we'll bring these like 5 and 2 under control, and then we'll fix up our zoom level to begin with, so it's something a little more sort of sensible. So we're like looking maybe at 1 meter per, or I guess one arbitrary unit, but we're kind of treating it as meters now, per several hundred pixels, or like 64 or 128 pixels or something. So what we need to do is find the zoom level and figure out what zoom level we want. So it's 2 to the something divided by 2, and so if we want 128, for example, that would be, do the maths in our heads, 2, 4, 8, 16, 64, 32, 64, 128, so that's 7, so I think we need zoom level 14. So we'll try that and see if that does what we expect. Does it make sense what I just sort of did there?
Yeah. Although, I mean, we can manipulate. Can we not manipulate the zoom level?
Yeah, we can still scroll it in and out, but maybe we want to like start with something that we can feel a bit more real world about.
What? Maybe. Hold on. Oh yeah. Yeah,
Yes.
good numbers.
Yeah, so, and it helps to like work in sort of fairly real world units. I may even say maybe we'll zoom that out just a smidgen to start with. Maybe we'll start with the zoom level 12, which gives us a bit more of a zoomed out feel. Okay, so that's that sorted, and that will let us sort of. I guess we'll feel better about what we're going to do next. So, what I wanted to do today was, you'll recall that we were talking about. Did I set up my brush for this? Oh my god! It saved my brush settings. I'm astonished. It's never done that before. Okay, so what we were talking about the other day, we ended up in the place where we had this equation, S equals ut plus, it's like, we'll do a cursive t so we can actually read the damn thing, ut plus half a t squared. So that's the equation we ended up with. And we're fairly happy about how we arrived at that through integrating. Yes?
Yeah. Mm-hmm.
And then we.
I wouldn't say happy, but we did do that last time. There's a yes. Yeah.
Okay. And so what we also had is we had this Wikipedia page for the equations of motion. And, we scroll down here, and it gives us, like the high school physics version of this. So we've got equation number 2 is what we end up with. We also, equation number 1, we also came up with ourselves. So if you remember, we had a constant acceleration a, and then we integrated up and we got velocity equals at plus a constant u. And so we ended up with equation 1. Then we integrated it up again, and we ended up with position equals initial velocity times time plus half acceleration times time squared plus the constant, which they're leaving off here. So this is where we end up as the first two, and then using a bit of algebra, you can get 3, 4, and 5. I believe that's the case. I don't think there's any more calculus going on to get these three. So
Right.
Hopefully that all makes sense, and that's just the same image zoomed up. So we can do some operations with this, and you no questions about that?
No, I mean, like you said, there's no more. If there's no more calculus to do, then I mean, this looks like that stuff like factoring that I'm algebraic factoring and moving stuff around to get the things you need.
Mm-hmm. Okay.
Not my favorite thing, but I know what I mean. Yes.
Yep.
I know what it is.
Excellent. So, what we want to do, and I'm going to see if I can maybe I can screenshot this screen and just paste it into our thingy here. Bear with me while I do a bit of image editing. Sorry, I've completely forgotten how to use my Paint program. Let's see. Layer, crop to selection. There we go. Okay, so now we have our things, and I'm going to sit them off in this corner up here so that we have access to them when we need them. Okay, so what we want to do now is, we were talking about this yesterday. I think we were still on stream when we were talking about this, and that is, we were talking about in River City. We have the one of the enemies has these like projectiles, and what happens is, and we do this in 3D space, but we're obviously in 2D space. But what he does is he lobs them to hit some particular target, like X marks the spot. And so what I think we should do today is we should try to re-implement this function here. And so what happens is it breaks down into basically the reason we want to do this in one sense is we have down here, we have this arbitrarily selected initial velocity. It's just like, well, that's just what we're going to start with. So it's like, what if we want to figure out what initial velocity to use? So that's what we're figuring out here, is what are we going to use for this vector here that determines where we start. Make sense?
Mm-hmm.
So this breaks down into whoops, what happened there? There we go. This breaks down into a couple of parts. Basically, we want to, like, we could do it in a single step and we'd end up with something that would look like a, I guess, direct.
Right, because you're not counting for the fact that you want to reach a certain height first and then hit the target.
Yep. So we want to go up some distance. There's actually, now this is a bit sort of more, I guess, involved, and that is, if you have if you don't try to reach a particular height, and I think I've got this correct. If you don't try and reach a particular height, you've actually got the ability to have many different arcs. So, for example, you could just fire this at like ridiculous speed like that, if that's your vector, and then this is like boop, 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 it's going to run into that almost immediately. Or you could end up having to like fire it like that with like a tiny little bit of velocity, and just it's going to go much slower, but it's going to arc and hit it. Whereas if we want to hit a particular point, we actually have to use a very specific single velocity to hit this thing and this point. And this all falls out of the fact that that's sort of the number of variables we have.
Right, and in hitting a particular point is just artistic, right? I mean, at the end of the day, like there's no reason other than you want to make a nice lobbing effect, right?
Well,
like there's no physical principle that would allow you to hit that height first. Like, I guess depend on the properties of your game objects. Like,
yeah, it's nothing to do with the maths certainly. There's no sort of requirement to do it. Except for the fact that by trying to hit 2 points, or at least a height and a specific point, you end up in a situation where all of these numbers come out. If you try and hit a point and you're not trying to go a specific height, you actually end up in a case where you have one variable left over, and so you can arbitrarily choose that variable still. And so that's why both of these, the orange one and the pink one, will hit this point. And all of the possible vectors in between, and even all, like you'll end up being able to use a whole lot of vectors.
Right.
But yeah, if you're in like a gameplay scenario and you've got like a wall or something there that you need to get over, like so if you're making like a like a tank game, with a tank with a turret, or what's that thing like worms?
Angry Birds. Oh yeah, Worms.
I love Worms. Worms was such a great game. Okay, so we're going to try and do this one. And so how do you feel about trying to do some of this algebra yourself, or how would you rather I just try and run through it on the whiteboard?
We can suffer together.
Okay. So I guess the first question would be, okay, so we're going to break this down into two parts. So the first part is, let's just try and hit a particular height. So we want to hit this height here, and we're going to ignore the x-axis for now. So we're just thinking about the y-axis. And so you can imagine this problem in one dimension is, we've got this thing, we're going to lob it up some distance, and we're going to hit some height and then come back down again. So up and then down. So the first question is, what equation do you reckon we're going to be using out of our little set of 5 over here to figure this out? And sort of, I guess just let me know where you're at as far as this goes. So take some time to think about that.
Right.
And let me know.
Well, we're trying to find an initial velocity, so we're trying to find u that's going to hit the point. So that probably removes the 3s algorithms, functions, because those s's are for position. So that leaves us with either the first one or the fourth one.
Well, what I'll point out is the first one and the fourth one, these are actually v's rather than u's. Like the u is further into the equation. So the thing is, they all, I think, have, except for the last one, they all actually have u's in them. So you could rearrange all of these as well.
Yeah, I forgot about that. Yeah, good point. Okay, well, so we know that we want the left side to be u, and we probably going to need acceleration, which eliminates the third one, because we're going to need to, it's like a thruster, and we need to know what the thruster is to hit that velocity, to hit that height. And so I'm just trying to think, where does u is u is the initial velocity, t is time, so time's obviously involved. Well, is it?
Well, no, actually.
No, it's not. Yeah, I just don't care about t. T is arbitrary. So that means I'm just gonna say, I think it's the fourth one.
Yes, that's absolutely correct. So we don't care about t, but you'll notice number 4 also has this s here, and s, of course, is how high is this damn thing?
Yeah, that's the resting place, I guess, that we're going to reach.
So let's see. So yeah, an acceleration will become, g for gravity. So now we need to rearrange this.
Yeah.
To get u at the other end.
Right.
How comfortable are you with that?
I can try. I mean,
give it a go.
So, all right. Well, I can't control anything, but I want to.
I mean, you could, if you like, I can switch over to your screen and you can try and type it.
No, it's okay.
I'll scribe for you. Yep.
Well, I want to move the u. I want to move the u squared over to the left. So I think when you do that, I think you flip the sign and put it on the other side.
Okay, so that would be.
So v2 times u times negative u squared plus is equal to 2as.
So let me help you out here. So each I forget what we call these, like each.
Oh, I could actually just move the 2as over and then just flip them around.
Yeah, so that's what I'm gonna do in a second.
That's better because that does follow the plus sign rule that I was thinking of.
Yeah, so you'll notice like there's this like hidden plus sign for the 2u. So you could move it, but then you just get v squared minus u squared.
Yeah, exactly. So throw the 2as on the other side, and then you can.
2as equals.
And then you could even reverse that, but who cares?
Yep.
So now I got to get rid of this squared. So I need to root the u, root the 2, and root the v, and root the 2as, I guess.
So I mean, this is fairly straightforward. So v squared minus 2as. And then these two cancel, of course, and we get.
So that's u is equal to v. Oh yeah.
So I was just finishing that off because I mean this is just copying that same thing down.
Yeah. Can we compress that further though? Can we get rid of the
No, we can't. I don't think so.
It can't be v minus the root of negative 2as?
No, so because this is a minus, if this was a multiply, so if we had like square root of 2as, we could break that down into like square root of 2, square root of a, square root of s. But because of a plus or a minus, will effectively block that from happening.
Makes sense, yeah. Welcome to grade 10 math. Yeah, okay. That's literally the last time I did that was... Okay, so there we go.
Okay, so let me think. I'm just trying to think whether we can just go straight into using this. I think we can.
We need to store this, don't we, somewhere now? Or can keep it in draw? Well, we need to know the height and then decide from there.
So what I think we'll do is we'll say, we have a shape. And we have the function that does, we have, what is it, this one here that actually does the animation for us.
Mm-hmm.
And so what we might do is we'll say, all right, S is now going to be where the cursor is. And so, and of course, eventually we'll put the cursor here and have a fixed height. Actually, no, maybe we'll start with a fixed height from this. So we'll just arbitrarily pick a height to go up. And then we'll make this the cursor when we actually do the next step. So we'll ignore this cursor here. So
okay.
So that's going to be an arbitrary choice. So we'll just say we go up I don't know 2 meters. So let's basically plug this formula in and program this up. So I will just type that down so we have it for reference. So what have we got? We're trying to get initial velocity.
Yeah. Fake one. Oh, you have it in there. One.
And we wanted to do u equals square root of v squared plus 2as was what we came up with on the whiteboard.
Yeah, right. So
I'll hand that to you.
Oh, this shouldn't. This is sorry, stupid. Just
So,
checking this stupid X and A thing. There's a math helper. It's not particularly better than. Oh, it doesn't
it
even have that in
yeah,
there.
it just has different things. I just thought of one thing, and that is we still have this is going to be one of these cases where we're going to want to do this. We're going to want to go just zero out the x-axis, and then so we'll just work in there.
Oh. Yep. Right, because we're on. Yeah. Okay. Sure. Makes sense.
Oh, we can leave acceleration up here. Yeah, that's fine. I guess yeah, you'll just have to go acceleration dot y, or in fact you could just write float g equals negative 9.8 f if you were so inclined.
Sure.
That's reasonable.
Sorry, just let me. I'm staring here for no reason. Okay, there we go. What is B? So we're missing V.
We missed a step. We missed a minor step. And a kind of an important step. So you're quite right. I've completely forgot to actually talk about this. Let's bring it back to the whiteboard and just have a quick chat.
What is V? V of t is at plus u.
Yep.
So, there is no v in. Oh, v is yeah. So, v
so
of t.
u is
initial velocity, and v is
v.
I forget.
Well, we haven't really talked about that, and that is
velocity at time t. Okay, so that is at plus u.
However, well, I'm just trying to think. I think we end up with something a non sequitur if we try and plug this in. I mean, and again, like we could rearrange this and plug this in just as easily.
Right.
So velocity at time t. I mean, this doesn't have a t in it, but it kind of does. And it's like, what is the time that we care about it? So at time t, we have at s of t, we want the position to be here. So at s of t, the position is here. For some t equals, I don't know, star. So at t star, so at s of this green star, that's the position. And so we also want to know when we're here at time green star, what is the velocity at time green star equals something. And what happens there is that's an arbitrary choice.
What? Sorry, not v star, vt star, right? Not.
So this is a function v that tells us the velocity at any given time. And I mean, And
Yeah.
And so sense. At this magical time star, so at the time we have sort of arbitrarily chosen, we want it to hit this point, and we want it to have a specific velocity at this time. We can arbitrarily choose this velocity, I guess is the conclusion of that.
Yeah, isn't that the velocity to hit? Like that's the velocity that we want to reach. So that's what the user input, the user data, the game data. Just I want to hit that point.
So well, this is the thing, and that is we can choose any velocity. So we could say that we want to hit point S at time star, or I guess because this doesn't have a time value, like the time star is kind of a misnomer. It's just at some point, any point, we don't care what point, we want to hit point S. If we just have like a ridiculous velocity, like, a bajillion, we can just go straight up and we will hit point S. And, we'll hit it. Simple as that. But if we actually want to hit it and then come back down, straight back down, we need to have a very specific velocity because we want to basically stop here and then come back down. And by stopping there, we have a velocity of 0. Does that make sense?
Mm-hmm. Sort of, yeah.
I mean, and when we start animating this, I think this might make a bit more sense too. But yeah, so velocity is going to be...
I get it. I mean, I can see it in my head. Like, I can get, like...
Yep.
It's like any game have a character, it jumps, but when it reaches the apex of the jump, the velocity is 0.
Mm-hmm. And so that's...
And
that's exactly what we want down in our little equation here. So
we don't know what the velocity is going to be.
Well, we don't know what the initial one is, but we know what the final one is.
Yeah, but it's arbitrary, right? It's whatever we want it to be.
Yeah, exactly. So we could say, we want to hit this point S, so we can use the same equation. We want to hit this point S, but we still want to be going at like, I'll put my thing down, at like, at some velocity going this way or something, for example. Now, of course, we have this square root here, and so what could happen is, if actually, like this is a really good point, is if we wanted to hit this point here with a velocity going like down, that's kind of obviously impossible. Actually, no, that doesn't work out. Because we'd end up coming straight up. Maybe we'll leave that for now, but it's basically a problem of, what happens if you end up with a negative number in here. Yeah, I'm gonna let that sit for now. But obviously, you can't get a sensible value if we were to try square root of like -1. We'd be like, that's an imaginary number. We can't represent that or do physics with it particularly sensibly. But I don't want to go down that rat hole today. But yeah, you can't take a square root of a negative number. So you can get nonsense out the other end of this if you, for example, try and get something nonsensical.
Wait, how do you do that? Oh no, it's math pow.
Well, so what we've just determined is v equals 0 and s equals 2.
Sorry, what? How did we decide v is 0? I thought we arbitrarily. Oh, that's the target. The target is 0. Yeah. Okay.
Yep. And then we've got our 2 over here.
How'd you get the 2?
That one is arbitrary. That is how high do we want to go over? Like if we have a wall, how high is our wall, for example?
Oh yeah. Okay, so I just did it wrong. I was just like, well, this is how high the wall is, but I was thinking 2 dimensions, and we're not in 2 dimensions right now.
Yes,
right.
Not yet.
So hold on, I'm having a fun time here.
That's all right.
I mean, this is not 2, so this will be v, which is 0. No, this is 0, but root of 0. Why isn't it like that? Oh, because it's a double or a float. I mean it.
So I mean, you're not wrong here. I'm just gonna help you out here and point out that v squared is obviously v times v, which is going to be 0 times 0.
Yeah, but I didn't want to lie to anything. But
Fair enough.
I guess
okay.
I could. V times v is probably smarter or easier to read.
I mean, that's probably like that's how I do it. In any case, using power is obviously quite slow.
Didn't know that. Obviously, yeah, this is going to be pretty compiler happy. Okay, hold on. I'm still square root of v. Right, square root of v squared plus 2 times as. Oh, what is A? A is
Well,
A.
A is going to be our gravity.
Yeah. Well. Yeah. Right. Again, it's not 2 dimensions. It's 1. So, right. That's A, and then S is going to be 2 because we decided it is.
Mm-hmm.
Sure if I need these scoping lines or not. Probably not.
No, so multiplication associates.
Um,
So I mean that's looking pretty good. So we had an arbitrary initial velocity, and now we have a very carefully calculated initial velocity that's going to go up these 2 units.
right. I guess I'm gonna run it. I don't know.
Let's give this a go. Let's see if it goes up about 2 meters, which is going to be, I think, like 128 pixels. Well, either I've made a mistake, but
Nothing's happening.
holding down space
Oh.
and nothing's happening.
That's probably because our S is just the old S. No, I mean we calculated the U. That's all we were doing here. Did I accidentally replace any values? No.
Okay, so this is always fun. Let's do some debugging. Curious. I mean, this should be a constant, so we could just run it and see what it comes up with in the debugger.
Not a number.
You know what?
Is that because of the...
This is my fault. This is my fault. No, this is my fault. Sorry. Okay, let me show you the mistake that I've made. We'll come down here. Look, there's a dirty grey arrow pointing to it. This is the formula that we came up with when we did the algebra on the whiteboard. And then I transcribed it wrong up here. That should be a minus. And that should be a minus. And you see what happened is when you debug this, you got not a number. You know, this was N. And what that means is, you know, we had obviously gravity is negative, so this whole expression became negative. So the square root gave us a, you know, not a number result. So this negative here, you know, it combines with this negative gravity to give a positive result, which is what we want. So that was my fault for transcribing that wrong, but that's a thing that can happen fairly easily when you've got a square root in there. So let's try again.
Nice.
Yeah, up they go. And, you know, that looks pretty physical, doesn't it?
Mm-hmm.
Okay, so...
Almost like the universe is governed by laws.
It's really satisfying too, isn't it? When you actually it's like, wee.
Yeah, I could probably do this for a bunch of times.
So the next thing we're going to do, let me
Got to hit a point now.
Yes, so we need to hit a point. So we have where is the thing? There it is. Okay, so now it gets a little bit more complicated. So we've gone up to something, and now we have an initial velocity, and we know we're going to hit velocity 0 at some point here. Okay, so now we have to move into 2 dimensions. I'm going to redraw this diagram. So we start here, we go up, we hit a point there, we come down and hit a target. Now, there's going to be already something interesting we've kind of touched on at this point now, and that is...
That's kind of 3 dimensions, isn't it, at this point? Because, like, the arrow on the right is extending past the blue line.
Not 3 dimensions, but I think there's going to be three steps to this equation. So we have we have this one, and we're going to need to have another. I think we need to do 2 more equations to actually get out this thing, because we're going to have to work out basically this section. So we need to work out the section up to there, and then the section from there down to there, and then that one there. So we've got 3 sort of things to look at. Now, we already kind of touched on a problem, and that is what happens if this is pointing downwards, I guess. So you can imagine the situation if, say, our target is, let me draw this up here. If our target is, I'm going to use the red X for this again. If our target is up here, and we're trying to go 2 meters up to like there, and we're going to hit velocity equals 0 there, we're going to like lob it up there, and we're never going to reach our target. So we actually have to think about the physics of this and be like, all right, we actually need the maximum of these 2 points. So if our target is above our starting point, because here it's below, but if it's above, we actually need to go above the target to get a nice lob. Does that make sense?
Yeah, so there's right, in that case you would end up ignoring your initial target because it wouldn't be possible to hit otherwise.
Yeah, so I mean, not necessarily, I mean, not ignoring is maybe not the right word, but it would end up with like, let's take the square root of a negative value, and you'd get, well, in the case of floating point maths, you get not a number out the other end, and it would do what it did before. So let's just bang that in now. Now we have to actually think about what our target's going to be. So it doesn't have to be in the shape loop. We can just say, vector 2 target equals question mark, question mark, question mark. And we actually, I don't think we actually have to do anything for this because we already have it. And it's just going to be mouse world position. I think that's right. I think that's all we have to do. So let's do that. And then all we have to do there is say, we have to work out what the height above the, so this is this 2 here. So let's give this a name. And so do you want to try your hand at this bit of code?
Yeah, I mean, sure. Like it's like wait. Well, it's gone. Our arbitrary number is gone now, so I don't know what I'm maxing at this point.
Okay.
It's between. So there was a. Well, I know that this is involved, right? But I don't. Well, actually, I don't know if that's even in the right coordinate system or not. No, it is because it's world position. We already transform it right up there on the camera. Okay, so then that's the height under my mouse, and then it has to be, can't be a negative number. So I mean, I need well, wait. There is no green dot though. Like we don't have one anymore. We killed it.
So yeah, this is what we basically have is this is 2.
Yeah, we want to be higher than that. Oh well, I mean, yeah, but where did you get the 2 from? You just picked it out of the sky.
So that's picking out of the sky, and this distance here is, we're just going to arbitrarily pick this out of the sky as well and say that's 2. Let's say It could, but we could easily make it 3, I guess.
I don't really get that part,
but the velocities we want are the velocities starting from here. So this is going to there, or this is going to there. So we actually have to get either this green one or the orange one. And so the orange one is really the other question mark. So what you could say is what we really want is, oh, come on, there it is. Okay, what we really want is maximum of target y something 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 or 2.
okay. But can we give the 2 a value? So I don't think it's part of your actual equation. It's more just like,
yeah. So
I'm gonna call that whatever.
lob height perhaps.
Okay. Yeah, that's more gamey.
So that's going to be 2, and this is going to be target y plus 2. So and something else. So hopefully you can see
S0 height, or is it shape position y?
It's I guess it's more of like the wall height. Okay, so shape position. So I think shape position y is involved. So the thing is, this is shape position y is obviously here in world space. So this is like a space conversion. So the origin of the world is probably out here somewhere, for example. And this is somewhere in the world space, and this is somewhere in the world space. We're coming out some distance on x and some distance on y, but still, this is when we calculate the velocity, we want we just want to go 2 up from here. So what we're really doing is trying to figure out the relative distance from there to there. Does that make sense?
Yeah, but I still feel like I thought that's what I was doing, but obviously not. Well, no. Well, the relative distance, that means like, are we doing some kind of abs thing, or are we?
So relative distance generally means something like subtraction.
Yeah.
And so I think you're actually pretty much on the right track. I think that's all you have to do. You just have to change this plus. No, actually that was right, but change this plus to a minus.
Oh.
I think that's all you have to do.
Don't think of it that naturally. I was gonna I would have put this on the left and start with that and then remove. Oh no, that wouldn't have worked either. Yeah, no, this makes sense. Yeah, okay.
So that's that thing that we've been doing a whole lot of. It's actually kind of counterintuitive to internalize, but it's like end minus start equals the relative position of 2 things.
That's right.
So let's give that a go. Let's see if that does what we want it to do.
Okay. Well. Okay. We haven't done the X plane yet, but this will be fine.
Yeah. So well, you recall that we had to. Now, if you make multiple shapes, they go at different speeds, which is fun. Whereas if you move the mass below everything, they all go at the same speed because they're all trying to get above this y position. Whereas if you move the mouse above them, they all try and get up to the same height and then fall. God, that's satisfying.
That's pretty cool.
So yeah, so as I was saying, this is like
at a certain point.
Yeah.
At a certain point, their futile desire gets beaten by gravity. It's like
exactly.
Sorry.
What's also interesting is obviously because this is functional and we haven't fixed the mouse cursor, we can move the mouse up and down and mess with them.
Yeah. That's how I discovered the Machiavellian bonus game.
Down you get. So we've got like this was so as I was saying, over where did I put this? Over did I erase it? I think I might have erased it. So we, as I was saying, we have like 3 parts to this thing. We have to figure out how do we get up to here. The next part is going to be how do we get, basically how long does it take to get down to here? And given the time it takes to get up to here, plus the time it takes to get down to here, how fast do we need to lob it? Like this way. Right. So that gives us the x-axis. So we've got like y part 1, and then y part 2, and then we have x over here. And then we had to figure out sort of y part 1.5. So we've done y part 1.5 and we've done y part 1. So I'm thinking that next time we'll come back and we'll finish off by doing y's part 2 and then x. And that will give us our full lob, and we can actually aim everything at a single point. Happy with that? Any questions before we wrap up?
No, I'm good.
Excellent. Okay, let me find OBS and turn it off. Thanks for watching, everyone.